I'd like to thank Professor Dong-Soo Kim and Professor Sang-Il for giving me the opportunity to present here. I think I present in this seminar too often. Hope you are not tired of me. So in this talk, I will introduce the permutation tableau, which is relatively new combinatorial object coming from a study of algebraic geometry. So let me just start with the definition of permutation tableau. So this is an example of a permutation tableau. So to define a permutation tableau, we need to first define a partition. So an integer partition was some with or we sometimes will omit this integer. Lambda is a weakly decreasing sequence of a non-negative integer. Usually, partition is defined by to be a weakly decreasing sequence of positive integers, but we allow zeros. So we may have zeros at the end. For example, 5, 4, 4, 3, 1, 0, 0. This is an example of partition, and we can identify a partition in terms of so-called Ferris diagram. So the Ferris diagram of lambda is a diagram which is an arrangement of left justified arrangement of scale cells. So in each row we have 5 squares corresponding to this number, and 4, 3, 1, and 0, 0. Okay. So in this first diagram, we may have empty rows. Okay. So I will sometimes identify integer partition with this first diagram. Now the definition of permutation tableau is the following. So a permutation tableau of shape lambda. So lambda is a partition. Is a 0-1 filling of the first diagram of lambda with certain conditions, such that we have two conditions. First one, each column has at least 1, right? And second, there is no configuration like this. So we don't have this configuration, meaning it's not allowed to have 0, which has a 1 above it in the same column and 1 to the right, to the left of it in the same row. So if a 0-1 filling of a first diagram satisfies these two conditions, then it's a permutation tableau. Let's see here. So in each column, we have at least 1, 1. Okay? We may have several ones. Okay? And we may have a row without any 1. Okay? And in this first diagram, I define it in this way so that we don't have any empty column. But it's automatical from this condition because each column has at least 1, 1, meaning it does not have any empty column. So it satisfies this condition, and the second one, let's see. We don't have any of these configurations. So if this were 1, then it's not a permutation tableau because we have this forbidden configuration or this one. So if we have 1 here, then it's not because these 3 cells make that forbidden configuration. Okay? So this is the definition of permutation tableau, but if you see this definition, you may feel like it's very strange why we are studying this kind of, why we don't allow this configuration or something. But what I can say to you is that this purely combinatorial object is not just an arbitrarily defined object. It's coming from algebraic geometry. So the motivation of this, I will not say more about this, but it's a Postnikov study of totally non-negative Grassmannian. So he found a correspondence between totally non-negative Grassmannian cells and this kind of object. So I think it sounds pretty fancy, meaning I don't really understand this. So anyway, so we had a very good motivation, and it's purely combinatorial, and we want to study that combinatorial object. And surprisingly, there is also another connection between this permutation tableau and an important model in statistical physics called PASEP. So there's also a connection, with PASEP. It's a statistical physics model. It's an acronym of partially, okay, let me just write that. Partially asymmetric exclusion process. Okay. So the PASEP is a statistical physics model, and we can define it as actually a Markov chain. So a PASEP, let me define PASEP briefly. Oops. Actually, I couldn't sleep well for the last 2 nights. Sorry. PASEP is a Markov chain. Markov. Is it guys? Okay. MAR Markov. KOB. Okay. Thank you. Markov chain with 2 things. So the state. So we fix n, alpha, beta, and q, and n is just positive integer, and alpha and beta is just an integer from 1 to q. Just okay. State is the set of words, all words of length n with 2 letters. Empty particle or a particle, occupied particle. So a cell without any particle, or a cell occupied with a particle. Okay, and we can. So for example, this is a Markov state, one example of a state of this parcel. So you can think this, it's n. You can think this as a, we have n positions, and in each position we may have a particle or not. Okay? So these three positions are occupied by particles. And in each time, this state can be changed to another one with this probability. So each particle can move to the right or to the left, and we can, a particle may enter in this way, and a particle here may exit in this way. Okay? So it's partially asymmetric. So let's see. If we have this thing, so this is some word, we only focus on these two letters. And this particle may hop to the right. So this state can be changed to this state with some condition, with some probability, 1 over n plus 1, and this may change to this q over n plus 1. And a particle may enter in this way, so meaning this state is changed to this state with this probability alpha over n plus 1. And the particle at the end may exit to the right. So this one can be changed to this with this probability. So it's basically particles, moving particles with some certain probability. Okay?
So alpha, beta are numbers up to 1 or up to n? Or
the real numbers between 0 and 1.
1 or
1.
n? Or is it 1?
1.
Okay.
Yeah. Okay. So, and so this is a simple model in the statistical physics, and there is a known fact. So what is known here is that if we observe this state in the very large, in the long time limit, we have the probability that we can find this special state depends only on these numbers. So meaning it has a limit. The probability that we can find this after some time, some sufficient time, then it has a limit. So they write in this way, in the long time limit, the system reaches a steady state. Okay, so we can write down the formula for the probability of this only in terms of these four numbers. And there is a theorem. And interesting thing here is that this probability, we can write this the probability of this in terms of permutation tableau. That's a surprising connection between this and that. So this
is state unique?
what do
the limit state, is it unique?
No, it can be anything, because this probability has some numbers.
So when alpha, beta, and q is fixed, then
Yeah.
the limit is unique?
Yes, because you can write the limit, the probability, only in terms of that number, so it's unique. Okay? And I will write the formula for the probability, only in terms of permutation tableau. It's purely combinatorial formula. So this is a theorem proved by Kotel, my co-author, and she's my boss currently. Cottel and Williams, 2007. We need some notations here. So, yeah. So lambda is a partition, and f lambda is the sum of T, it's permutation tableau of shape lambda, this shape. So we add consider all the permutation tableau with this given shape, and we add this Q to the superfluous of T. I will define this terminology later. U R R of T. They are very simple quantity in permutation tableau. Tab 1T. So this number. And f of n. Sorry, I forget one thing. The length of this partition or Ferris diagram is the number of, so the length of lambda is the number of rows plus number of columns, right? So it's just the number of steps if you read in this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The length is 12, okay? So number of rows plus number of columns. So Fn is the sum of lambda. It means the lambda is a partition of n, and F lambda, right? Then their theorem says that the probability that, so tau, so this is a tau, the probability that we can find this state in the long time limit. And you may notice this, but we can identify tau as a Ferris diagram. Can you see that? So you can consider this as a sequence of 0 and 1, right? And for each 0 and 1, if it's 0, then we draw this step. If it's 1, we draw this step. Okay, 1, 0, 1, 1, 0, 1, 0. Okay? You can see some partitions here. But we have to add one step, extra step here, to make sure that we don't have any empty column. So we add one, add it. Okay? And then we make the Ferris diagram. Okay? So tau corresponds to this partition. Okay? So this state, you can read it as a partition. All right? Then this one is very simple. F lambda over Fn. The probability, you can write it only in terms of permutation tableau. All right? They prove this using so-called matrix ansatz, something. So we need to define these three statistics. That is, okay, I will delete this. Okay.
But if all alpha, beta, q are 1, then it's counting.
Yeah, it's just the number of permutation tableau of shape lambda divided by the n factor. Oh, I didn't mention this. But if you can guess that it's called permutation tableau, you can guess that it's closely related to permutations. Actually, there is a bijection between these and permutation tableaus. So the number of permutation tableau of length n is n factorial. So if, like Professor said, if these are all 1, then this number is just n factorial of a number of permutation tableaus of shape lambda. So let me define those three terms. Okay. So superfluous ones. Okay, let's say just superfluous. No. Superfluous 1 of T. So 1 in this permutation tableau, A1 is called superfluous if it is not the topmost one. Topmost one in the column. Right? So, for example, this is a superfluous one because it's not the topmost one. So the superfluous ones in this example are exactly these two. Okay. And a 0 is called restricted if it has a 1 above it. Okay? So if it's restricted, it has a 1 above it, forces us to fill all these cells with 0. So this is why it's called restricted. If yeah, there is yeah, I don't need to write the whole sentence. Okay, and a column, no, a row is called restricted if it has a restricted 0. So, for example, yeah. So let's say these are restricted. Let's find restricted zeros. So restricted, restricted, restricted. All right. So unrestricted, and if it's not restricted, then it's unrestricted. So otherwise it's called unrestricted. Okay. So URR of T is the unrestricted number of unrestricted rows, number of unrestricted rows, but -1. So -1 we subtract by 1 because we don't want to consider the first row. The first row is always unrestricted. It's always unrestricted. Okay, so the last one, top one, is simple. The number of ones in the first row. Okay, so these are the topmost ones. Okay, very simple statistics. So in this example, URR of T, unrestricted rows. So these are the unrestricted rows, but we have to discard this one, so it's 2. Superfluous 1 of T equals 2. Top 1 of T, 1 to 3. Okay?
So that's the number of superfluous 1?
Yes. Oh yeah, sorry, I didn't write the superfluous 1 of T, the number of superfluous ones. Okay? So, purely combinatorial sum. It says some interesting model. You can study some interesting model with this combinatorial object. So now you can see that it's worth studying permutation tableau, all right? Its connection with algebraic geometry, statistical physics, and of course combinatorics. So we will focus on the combinatorics of this permutation tableau. All right. So this formula is especially interesting. F sub n is the sum of this number, this quantity, for all permutation tableau of length n. Okay? And if there is a theorem
Is it length n or is it partition of n?
length n.
So that notation.
Yeah. Oh, sorry. Yeah, you're right. Yeah, lambda. Okay, length of lambda is n. Yeah. Thank you. All right. So, there is an interesting, very simple and elegant formula for this summation when q equals 1. So we only consider the theorem by Gotel and Nadu, also 2007. So Pt of n is the set of permutation tableaus of length n. Okay? So we are considering that sum. X to the unrestricted row of T and Y to the top one of T. So it's just that formula with Q equals 1. Okay? And this summation has a very nice, it's very simple actually. It's X plus Y n minus 1. It's the rising factorial of this number. So it means that x plus 1, x plus y plus 1 up to x plus y plus n minus 1. So in total we have n terms. Okay.
N minus 1 maybe?
Oh yeah, n minus 1.
And n minus 2.
That's right. So x rising factorial is called rising. Is it right? Rising factorial is called rising factorial. And so x plus 1, x plus n minus 1. So we have terms increased by 1. So of course n1 rising factorial of n is n factorial, and 2 is or n factorial. Okay. So if x equals y equals 1 is 2 rising factorial up to n minus 1, which is n factorial. So it's counts the same number as the permutation. And they proved this using by finding a recurrence relation, and we proved this combinatorially using some bijection. So let me present a bijection between permutation tableau and permutation. And in fact, there are many bijections between permutations and permutation tableaus, like I think more than or almost 10 bijections. And so this is one of the bijections which I like the most. And this permutation tableau, we can consider, we have another representation of this permutation tableau which may look simpler. So I will write this in alternative representation. In this representation, I will erase all the zeros and ones, and I will fill the cells with arrows. So it's very simple. Change the topmost one to these up arrows, and rightmost restricted zeros to this arrow. So we have two kinds of arrows. All right? So let's see what happens with this example. It's a okay. I draw the same shape, and the topmost ones are these. The topmost one, they are the topmost one in this column. So I change these with up arrows. Up, 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 up. Yeah, I forgot this. Up. And these are the restricted zeros, and these are the rightmost restricted zeros. These are the rightmost restricted zeros. I change this to this. These are another representation. Do you see any property of this diagram? There is no arrow pointing to another arrow. Right? If you have this arrow, there's nothing. It points nothing. And each column has exactly one up arrow. Those two are the only conditions for this alternative representation. Yeah, maybe it's simpler than that. And we can recover this from this the alternative representation, because these are all ones and these are zero. And because of condition, we fill all the empty cells which has an arrow pointing to itself with 0, and other empty cells with 1. Then we can recover this original permutation tableau. So this alternative representation. Okay, so they are the same, just another representation. And so you may wonder what those integers mean. And I write this, I label the rows and columns in this way. So we travel this border from this corner to this, and write this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And these labels are those correspond to the step label. Okay. Right. Then let me briefly define the bijection between this and permutation tableau. I will use this because it's simpler to describe. Okay. Yeah, I will let's erase this. Okay. So from this tableau, we will find the permutation. The correspondence is this. We first find the unrestricted rows. So these are the unrestricted rows. I have checked that. Unrestricted rows. So first we arrange these integers in increasing order. So 1, 10, 13. Okay, this is the first step. And we will look at each column from the left to right. Okay. Each column look like this. Looks like each column has exactly one up arrow. So we have some up arrow in this way. And there's nothing above it. And we may have some left arrows below this top arrow, okay? Maybe we may not have anything else here. So this, let's see the labels of this. So this row label is like A, let's say B, C, D, and E. Okay? So the column label and the row labels of this, and there is this. Okay? And then we will write in this way. If we have this situation, then A must be already written there. So we will write E here before A, and then B, C, D before E. We will write in this way. So let's see this example. So we have this column, 10, 12, the column 12 column labeled with 12 has a up arrow in this column, this row. So we add 12 before 10. Okay, and we have this 11. So we put 11 before 10, 12. Okay, we proceed this. 9 at this row 1. So 9 is placed right before 1. And next, 8 is before 1. So we have to put 8 here. So let me just put this in this way. 8, all right? 2, 7. 2, 7 in increasing order before 8. And here, 6, 2. So 6 is before 2. 6, let me just write here. 6 before 2, and 4 before 6. Okay. And 5 before 2. Right. 5. 3 before 1. 3. So we get a permutation. And in fact, this is a bijection. From this permutation, we can recover this. It's a little more complicated, but it's not that complicated. In fact, it's easy to describe the inverse map, but I don't think I have enough time, so let me just write this. So using this bijection, I and CD proved this formula unrestricted. What was that? Total top 1. We proved this combinatorially regarding x and y as positive integers. If x and y are positive integers, they both count something, and we just found a bijection between these objects and these objects. So we proved that combinatorially. And our proof allowed us to consider another statistic of this permutation tableau, which we call unrestricted columns instead of unrestricted rows. So that is So let me recall the definition of unrestricted row. Unrestricted row is a row without row. We don't have this 0, which has 1 above it. So this row is unrestricted if we don't have this situation. Okay? So we can consider unrestricted column in the same way. So this column is unrestricted if no this situation 1, 1. Okay? So unrestricted columns is kind of natural way to consider compared to unrestricted rows. And we considered this number, this quantity. So permutation tableau of T and T to the number of unrestricted column. So here, unrestricted, it means the number of unrestricted columns in T. Okay? We don't delete anything here. And I didn't present our proof, but our proof allows us to compute this. And let me write the formula. It's, let's say it's Cn of T, and the theorem is that myself, we in fact computed the generating function for this quantity. Cn of T x to the n is 1 plus et of x, 1 plus t minus 1 x times et of x, where et of x is this. And from 1 n times t rising factorial. All right. So if t equals 1, then it's just the number of permutation tableau, which is n factorial. So if t equals 1, the denominator is 1, then here 1 plus this n factorial. Right? And there are two interesting subcases of this theorem. So the corollary, if t equals 2, so t equals 1 is also it's a trivial subcase, but t equals 2, then we have this corollary. We can compute this number, this generating function. It has a simple generating function formula. All right. And in fact, this generating function counts something else. It is known that it's the generating function for the number of connected permutations of integers from 1 up to n. A permutation is called connected if so pi is called connected if each purpose prefix is not a permutation. For example, let's see, 3, 1, 4, 2, 5, 6, 7, 8. This is not a connected permutation because if we consider this prefix, which is not the whole permutation, it becomes a permutation. If we don't have this kind of prefix, then it's called connected. So we cannot divide any subord. So we count some interesting number. And in fact, we prove this combinatorially. And there's more